The assumption that the amperage is evenly divided amongst the paralleled conductors is based on the principle of balanced loads. In a balanced three-phase system, the current in each phase should be equal in magnitude and phase angle. This ensures that the neutral conductor carries minimal current and that the voltage across each phase is approximately equal. In practice, it is not always possible to achieve perfect balance, but the closer the system is to being balanced, the more evenly the current will be divided among the paralleled conductors. The capacity at which each 4/0 American wire gauge conductor will realize is determined by the ampacity of the conductor, which is the maximum current that the conductor can safely carry without overheating. The ampacity of a conductor is dependent on its size, material, and temperature rating as listed in the National Electrical Code, or NEC. In the case of 4/0 American wire gauge conductors with a 75°C temperature rating, the ampacity is typically 200 amps per conductor, according to NEC Table 310.15b16. This means that each conductor can safely carry up to 200 amps of current, assuming standard installation conditions. It is possible for one phase to overheat if the current is not evenly divided among the paralleled conductors. This can happen if one conductor is damaged, has a higher resistance than the other conductors, or the connections between the paralleled conductors are not properly torqued, which can increase resistance at the termination points. In this case, the current will flow preferentially through the conductor with the low resistance, causing it to overheat. To prevent this from happening, it is important to ensure that the paralleled conductors are of equal length, material, termination, and have the same resistance. It is also important to make sure that the connections between the conductors are tight and secure, and torqued according to manufacturer specifications using a calibrated torque wrench. Paralleling conductors requires careful attention to detail to ensure proper current sharing and prevent overheating. Here are key factors that influence current distribution and how to mitigate potential issues. Firstly, conductor length. Unequal lengths introduce different impedance levels, leading to uneven current sharing. Always ensure conductors are cut to the exact same length. Secondly, conductor material and size. Using conductors of different materials or sizes will result in differing resistances. All paralleled conductors must be of the same material and size. Thirdly, termination quality. Poor connections can create hotspots and increase resistance. Use properly sized connectors, clean the conductors before termination, and torque connections to the manufacturer's specifications. Fourthly, proximity effect. Conductors that are closer together experience a greater magnetic field interaction affecting impedance. Space conductors evenly apart to minimize proximity effects. Fifthly, skin effect. At higher frequencies, current tends to flow closer to the surface of the conductor. While less significant at 60 Hz power frequencies, it is still a factor. Using larger conductors can help reduce the impact. Sixthly, impedance balancing. Implement measures to balance impedance, such as transposition, where conductors are periodically swapped to equalize impedance. Seventhly, monitoring and maintenance. Regularly inspect connections and conductors for signs of overheating or corrosion. Use thermal imaging to identify hotspots early on. Eighthly, conductor bundling. Avoid tightly bundling conductors, as this can restrict heat dissipation. Maintain adequate spacing for airflow. Ninthly, directing factors. Be aware of ambient temperature and other directing factors that can affect conductor ampacity. Adjust conductor size accordingly. Tenthly, NEC compliance. Adhere to NEC guidelines for paralleling conductors, including requirements for conductor size, material, and termination. Now let's dive into a more comprehensive exploration of the factors that influence current distribution in paralleled conductors and the engineering principles behind ensuring balanced operation. Consider that the foundational concept behind paralleling conductors is based on the principle that conductors connected in parallel share the total current load inversely proportional to their individual impedances. In an ideal scenario, where all paralleled conductors possess identical characteristics, the current divides equally among them. However, in real-world applications, several factors can disrupt this equilibrium, leading to unequal current distribution and potential hazards. Firstly, let's discuss conductor impedance. Impedance, denoted as Z, is the total opposition a conductor presents to alternating current flow comprising both resistance R and reactance X. In parallel conductors, even slight variations in impedance can significantly impact current sharing. Resistance arises from the conductor's material properties, length, and cross-sectional area. According to Ohm's law, resistance is directly proportional to length and inversely proportional to cross-sectional area. Therefore, conductors of unequal lengths or varying cross-sectional areas will exhibit different resistances, leading to unequal current distribution. Reactance, on the other hand, is the opposition to current flow due to inductance XL and capacitance XC. Inductive reactance increases with frequency and inductance, while capacitive reactance decreases with frequency and capacitance. In parallel conductors, inductive reactance is more prevalent due to the magnetic fields generated by alternating current flow. Unequal spacing between conductors or variations in conductor geometry can introduce differences in inductance, resulting in unequal inductive reactance and uneven current sharing. Secondly, let's discuss conductor length. As previously mentioned, conductor length directly influences resistance. Even minor discrepancies in length can lead to significant differences in resistance, especially in long conductor runs. To mitigate this effect, it is crucial to ensure that all parallel conductors are cut to the exact same length. Precision in cutting and routing conductors is paramount to achieving balanced current distribution. Thirdly, let's discuss conductor material and size. The material and size of the conductor dictate its inherent resistance and ampacity. Using conductors of different materials, such as copper and aluminum, or varying sizes, will inevitably result in unequal current sharing. Copper conductors typically exhibit low resistance compared to aluminum conductors for a given size. Therefore, mixing conductor materials in parallel configurations is generally not recommended. Furthermore, the American wire gauge, or AUG, size of the conductor determines its cross-sectional area and ampacity. Larger conductors have lower resistance and higher ampacity compared to smaller conductors. Consequently, using conductors of different AWG sizes in parallel will lead to unequal current distribution and potential overloading of the smaller conductors. Fourthly, let's discuss termination quality. Proper termination techniques are essential for ensuring low resistance connections between conductors and equipment. Poorly executed terminations can introduce additional resistance, leading to localized heating and voltage drop. Over time, these issues can exacerbate, causing premature failure of the connection and potential hazards. To ensure reliable terminations, it is crucial to use properly sized connectors, clean the conductors before termination, and torque connections to the manufacturer's specifications using a calibrated torque wrench. Additionally, regular inspection and maintenance of terminations are necessary to detect and address any signs of degradation or corrosion. Fifthly, let's discuss proximity effect. The proximity effect refers to the redistribution of current density within a conductor due to the presence of nearby conductors carrying alternating current. When conductors are closely spaced, the magnetic fields generated by each conductor interact, causing the current to concentrate on the outer edges of the conductors. This phenomenon increases the effective resistance of the conductors and can lead to unequal current sharing in parallel configurations. To minimize the proximity effect, it is recommended to space conductors evenly apart and avoid tightly bundling them together. Adequate spacing allows for better heat dissipation and reduces magnetic field interaction, promoting more uniform current distribution. Sixthly, let's discuss skin effect. The skin effect is another phenomenon that affects current distribution in conductors carrying alternating current. At higher frequencies, current tends to flow closer to the surface of the conductor, rather than being uniformly distributed throughout its cross-sectional area. This effect increases the effective resistance of the conductor and can become significant at frequencies above the power frequency of 60 Hz. While the skin effect is less pronounced at 60 Hz, it can still contribute to an equal current sharing in parallel conductors, especially in larger conductors. To mitigate the skin effect, It is advisable to use larger conductors with a greater surface area or to employ specialized conductors designed to minimize skin effect losses. Seventhly, let's discuss impedance balancing. Impedance balancing techniques aim to equalize the impedance of parallel conductors to promote uniform current distribution. One common method is transposition, where conductors are periodically swapped or rotated to equalize inductance and minimize impedance imbalances. Transposition is particularly effective in long conductor runs where inductive reactance can vary significantly along the length of the conductors. By periodically transposing the conductors, the effects of inductive reactance are averaged out, resulting in more balanced current sharing. Eighthly, let's discuss monitoring and maintenance. Regular monitoring and maintenance are essential for ensuring the long-term reliability and performance of parallel conductor systems. Periodic inspections should be conducted to detect any signs of overheating, corrosion, or loose connections. Thermal imaging can be used to identify hotspots early on, allowing for timely intervention and preventing potential failures. Additionally, it is important to regularly torque connections to the manufacturer's specifications to maintain proper contact pressure and minimize resistance. Ninthly, let's discuss conductor bundling. Conductor bundling refers to the practice of grouping conductors together, either for convenience or space-saving purposes. However, tightly bundling conductors can restrict heat dissipation and exacerbate the effects of proximity and skin effects. To ensure adequate cooling and minimize current imbalances, it is recommended to maintain adequate spacing between conductors and avoid tightly bundling them together. Tenthly, let's discuss directing factors. Directing factors are adjustments applied to conductor ampacity to account for various environmental conditions and installation factors. Ambient temperature, conductor bundling, and conduit fill are common factors that can reduce the ampacity of conductors. It is essential to consider these directing factors when sizing parallel conductors to ensure that they can safely carry the intended load without overheating. 11th, let's discuss National Electric Code, or NEC, compliance. The NEC provides specific guidelines for paralleling conductors, including requirements for conductor size, material, termination, and overcurrent protection. Compliance with the NEC is essential for ensuring the safety and reliability of parallel conductor systems. The NEC mandates that parallel conductors must be of the same material, size, and length, and must be terminated in the same manner. Additionally, the NEC requires that each parallel conductor be protected by an individual overcurrent device, such as a fuse or circuit breaker, to prevent overloading and potential hazards. 12th, let's discuss overcurrent protection. Proper overcurrent protection is crucial for safeguarding parallel conductors against overloads and short circuits. Each parallel conductor must be protected by an individual overcurrent device sized according to its ampacity. The overcurrent devices must be coordinated to ensure that they trip selectively in the event of a fault, minimizing disruption to the electrical system. Additionally, it is important to consider the interrupting rating of the overcurrent devices to ensure that they can safely interrupt the fault current without failing. 13th, let's discuss voltage drop. Voltage drop refers to the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can lead to poor performance of equipment and potential damage to sensitive electronic devices. In parallel conductor systems, it is important to calculate the voltage drop to ensure that it remains within acceptable limits. The voltage drop can be calculated using Ohm's law, taking into account the conductor's resistance, length, and current. If the voltage drop exceeds the allowable limit, it may be necessary to increase the size of the conductors or reduce the length of the run. 14th, let's discuss harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as electronic devices and variable frequency drives. These harmonic currents can cause overheating of conductors and equipment, as well as interference with other electronic devices. In parallel conductor systems, it is important to mitigate the effects of harmonic currents by using harmonic filters or reactors. Harmonic filters are designed to block harmonic currents and prevent them from propagating throughout the electrical system. Reactors, on the other hand, are used to limit the magnitude of harmonic currents and reduce their impact on conductors and equipment. 15th, let's discuss neutral conductor sizing. In three-phase systems, the neutral conductor carries the imbalanced current between the phases. If the phases are perfectly balanced, the neutral conductor will carry no current. However, in real-world applications, the phases are rarely perfectly balanced, and the neutral conductor will carry some amount of current. In parallel conductor systems, it is important to properly size the neutral conductor to ensure that it can safely carry the unbalanced current without overheating. The NEC provides specific guidelines for sizing the neutral conductor based on the percentage of nonlinear loads connected to the system. 16th, let's discuss grounding. Proper grounding is essential for ensuring the safety of electrical systems and protecting against electric shock hazards. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent devices to trip and energize the circuit. In parallel conductor systems, it is important to properly ground all conductors and equipment to ensure that fault currents can flow safely and effectively. The grounding system must comply with the requirements of the NEC and other applicable standards. 17th, let's discuss labeling. Proper labeling is essential for identifying parallel conductors and ensuring that they are properly maintained and operated. Each parallel conductor must be labeled with its size, material, and ampacity. Additionally, the labeling must indicate that the conductors are connected in parallel and must provide information about the location of the overcurrent protection devices. Proper labeling helps to prevent confusion and ensures that maintenance personnel can safely and effectively work on the electrical system. 18th, let's discuss documentation. Complete and accurate documentation is essential for the long-term reliability and performance of parallel conductor systems. The documentation must include detailed drawings, specifications, and calculations for the conductors, terminations, and overcurrent protection devices. Additionally, the documentation must include records of all inspections, maintenance, and repairs performed on the system. Proper documentation helps to ensure that the electrical system can be safely and effectively operated and maintained throughout its lifespan. 19th, let's discuss future expansion. When designing parallel conductor systems, it is important to consider the potential for future expansion. The conductors and overcurrent protection devices must be sized to accommodate the anticipated load growth. Additionally, the system must be designed to allow for easy addition of new conductors and equipment. Considering future expansion helps to avoid costly and time-consuming modifications to the electrical system in the future. 20th, let's discuss professional expertise. Designing and installing parallel conductor systems requires specialized knowledge and expertise. It is important to engage qualified electrical engineers and contractors who have experience with parallel conductor systems. These professionals can ensure that the system is designed and installed in accordance with all applicable codes and standards, and that it will operate safely and reliably. In summary, parallel conductors offers numerous advantages, including increased ampacity, reduced voltage drop, and improved system reliability. However, it also presents several challenges, including the potential for unequal current distribution, overheating, and increased complexity. By carefully considering the factors discussed above and adhering to the guidelines provided by the NEC and other applicable standards, it is possible to design and install parallel conductor systems that are safe, reliable, and efficient.